Hello guys, welcome to NameTech channel. My name is Nehemiah and this is lesson 6 on Scipy. We are going to talk about spatial data. But then before we begin, please take a minute, subscribe, like and share the video to your friends if you have not done so. And to the returning subscribers, thank you very much for your continuous support. Without further ado, let's begin straight away. Now guys, basically spatial data refers to data that is represented in a geometrical space, like points on a coordinate system. And guys, this one is very important because it can help us find if a point is inside a boundary or not. And Scipy provides us with a module called Scipy.spatial, which has the function for working with spatial data. I'm going to show you an example in a few. Before then, let me talk about triangulation. Now guys, basically a triangulation of a polygon is to divide the polygon into multiple triangles with which we can compute an area of the polygon. And a triangulation on points means creating surface composed triangles in which all of the given points are on at least one vertex of any triangle in the surface. Now one method to generate this triangulation is through point is the delineate triangulation. Guys, I'm going to show you how to create a triangulation from some points. Before that, guys, ensure that you have installed some of the supported Matplotlib GUI for it to work, because for it to visualize, for it to draw those graphs. Now guys, once you have installed those packages, then guys, let me first of all, we are gonna import. Actually, we're gonna import three. We're going to write 3 lines to make our compiler be able to draw the graph. Now the first one is we are going to import SYS. This is the first module. And then the second one, let me say import now matplotlib. Ensure that you installed matplotlib. And then also we are going to import let me say matplotlib, and then now you're gonna use we are gonna use some first of all in quotes, then let me say tk then agg. And then now guys, basically these are just the lines to make our compiler be able to draw. Now the code for this example, it is import. First of all, we are going to import the numpy. Remember, Scipy is just a submodule of numpy. It is written under underneath numpy. So let me say now import numpy. Numpy is what? PD NP alias. Remember, PD is the alias for pandas, but then a default one for numpy is NP. And then now we're gonna import also another module from Scipy. So let me say from Scipy .spatial import. We're gonna import what? Delineate, and then also we're gonna import the last module is in pyplot. Import matplotlib dot pyplot. Matplotlib dot pyplot is a PLT alias, and then now guys, let me create here some numpy arrays. Let me say let me use a points. Let me give it points. Let me use a variable points. Then let me assign it to np dot array, numpy array. And then here I'm gonna create a 2-dimensional array with this array list here. And the first one, perhaps let me say 2 and 4. And then the second one, first of all a comma. Then the second one gives let me say perhaps 3 and 4. Then the third one gives the third array list. Let me say 3 and 0. Then the other one, let me say what? Not really, should be here 3 and 0, and also here let me say 2 and 2. 2 and 2, and then basically 2 and 2 and 2, and then the last one, let me say 4 and 1, 4 comma 1. Now this is the last one, we don't have to add the comma there. And then now guys, let me create now these let me say simplices, variable simplices. Then let me assign it to delineate like that. And then we are gonna pass inside it points, that variable of ours points, and then dot simplices dot simplices should be simplices. Basically guys, these are simplices method basically property creates the generalization of the triangle notation. Now once you've written that, then we're gonna now write the PLT now here. Let me say PLT dot triplot, and then we're gonna pass points. The first one, let me say perhaps to 0, then the second one, let's say points to, sorry, should be to perhaps something like 1 to be 1 to 1 to 1. And then guys, the other one I'm gonna use PLT scatter, but before that, let me add this argument guys. Let me add simplices, and then let me create also the other lines of code, PLT dots. Now I'm gonna use the scatter, and then points. In our case, let me just copy these lines of code. Let me copy, and then let me just paste it here. Then here the other argument, I'm gonna use color. Then let me assign it to R. And then what I do is to visualize, we use this function plt.show function. But then I'm gonna write now the other two lines to make our compiler be able to draw the graph. The last two lines of code, let me say plt dot save fig, and then let me pass in sys dot std out dot buffer. And dot buffer, basically this is the first line of code, the second last line of code. Then sys dot std out dot flash. And then what I do, let me run these codes. Let me run the codes, and then guys, basically you can see that we have done what we have drew this we have done what we have created this triangulation with those points there. Let me try to expand it. Guys, basically you can see that we have just created this stuff here. But then guys, let me now talk about convex hull. Now guys, basically a convex hull is the smallest polygon that covers all of the given points. Now basically guys, we use the convex hull method to create the convex hull. And guys, let me show you an example how to create a convex hull from some points. Now here we are going to change it to, we are going to change the module here to from delineate to what, to something else called convex. Should be convex hull, like this, convex hull. And then what is here the list guys, let me do it now. The list here, let me say perhaps let me add several lists, perhaps let me say 4 to 1. Then here let me add in another one like 1 to 2, and then the other one, let me say perhaps something like 5 and 0 comma sorry, comma, then the other one, let me say something like 3.1, comma, then the other one, let me say something like 1.2, and then here let me say what, let me say the last one, let me say 0, 0, 0, should be 0 and what, 0 and 2. This is the last one. You don't have to add the comma. Let me count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. I think they are correct. Then guys, what we do here, first of all guys, let me just delete these lines of code. Remember, these are the other 2 lines of code. These are the lines of code that help us to draw our basically to draw our graph. These are 2 lines of code here at the end. We don't have to delete it because I will just repeat ourselves. Let me now say hull, then I assign it to something like a convex hull method, a convex hull. Then I'm gonna pass in points. Remember, points is a variable that we defined it here for our numpy arrays. And then here let me say hull points, create another variable, hull underscore points, then let me assign it to hull dot simplices, then here let me say plt dot scatter. I'm gonna use a scatter distribution, scatter, then let me pass in points, and then the first one, let me say to 0, then the other one, let me say perhaps points to what, to perhaps let me say this one to 1. And then what I do, let me use the for statement here. Let me say for let me create simplex, for simplex in what, in hull underscore points, and this variable here, this variable underscore points, then a close, then here let me say plt dot plot points into simplex comma 0. And then the other one, let me just say let me just copy, and then guys, the other one, let me just say what, let me just copy to here. Let me just copy these codes, let me just copy, and then what I do guys, let me just paste it here, and then here instead of 0 I'm gonna change it to 1. Then let me add in another property here called k negative, and then guys, I guess the codes are okay. I guess the codes are very perfect. So what I do guys, to visualize, we use what, plt. We use a plt. First of all, let's remove the indentation there, basically the indentation. Then let me say plt dot show. Then guys, what I do, let me run these codes at the terminal. Let me run the codes. So guys, basically this is how you can do it. This is how you can create a convex hull from these points here. Now guys, let's now talk about KD trees. Now guys, basically KD trees are the data structure optimized for nearest neighbor queries. Like for example, in a set of points using KD trees, we can efficiently ask which points are nearest a certain given point. Now the KD3 method returns the KD3 object, and the query method returns the distance to the nearest neighbor and the location of the neighbors. Now guys, basically let me and there's a new line of code. Let me show you that example. First of all, we're going to import now that KD3 submodule. So from Scipy, basically Scipy from Scipy the spatial should be spatial. Then let me say import what KD3 module, and then here let me say points. Let me create here an array points, and then let me assign it to just a normal Python array. Then let me use an array list, basically a tuple. Let me use a tuple here. Let me say perhaps 1 comma, then perhaps -1, and then the other one, let me say perhaps something like let me say 2, then 3, and then the other one, let me say perhaps something like -2, 3. The other points, the other coordinate, let me say something like 2, and then -3. Then let me create here a variable, then I give it, let me say KD3 variable. You can use another variable name. Then let me assign it to KD3, and then we're gonna pass in points, actually this variable here. And then what we do, let's say, let me create another res, then let me assign it to k should be KD3 that variable, and then dot query should be query, right guys? I say that these are query method return the distance to the nearest neighbor and the location of the neighbors. And then the KD3 method, this one, basically this function return the KD3 object. Now what we do, let me close, and then let's find what the nearest distance, basically the distance to the nearest. Let's find the distance to the nearest neighbor and the location of the neighbors. Like for perhaps let me say 1 and 1 and 1. And then what we do, let me pass in what, to the print function, let's say print what we're gonna print. Let's print what this res. Then let me run, and so guys, basically you can see that the points which are near these ones is 2.0 and 0. So let me talk about distance matrix. And guys, basically there are many distance metrics used to find various types of distance between 2 points in data science, Euclidean distance, cosine distance, and so forth. Now guys, basically the distance between two vectors may not only be the length of the straight line between them, it can also be the angle between them from origin, or a number of unit steps required, and so forth. Now guys, basically many of the machine learning algorithms performance depend greatly on the distance metrics, like k nearest neighbors, or k means, and so forth. Now guys, let us look at some of the distance metrics. Let's begin with the Euclidean distance. Now guys, basically let me show an example guys how to find the Euclidean distance between some points. What we do now guys, let me show you an example guys how to find the Euclidean distance between given points. Now first of all, let me say from Scipy dot spatial should be t spatial dot distance import what we're gonna import Euclidean. Actually should be Euclidean. It should be Euclidean. And then guys, here let me create some 2 points. So the point 1, let me give it P1. Then let me assign it to something like 1 and 0. Then point 2, let me say perhaps P2. Then let me assign it to something like 10 and 2. And then let me now create a variable here. Let me give it just res. Then let me assign it to Euclidean. Then let me pass in P1 and P2. And then to the print function, let me say print what we're gonna print res. Then what I do, let me run the codes at the terminal. And then guys, I basically can see that it prints out a 2 point in this value. So guys, basically this is how you can find the Euclidean distance between given points. So guys, let me now talk about city block distance or Markham distance. So guys, basically this is the distance computed using 4 degrees of movement. Like we can only move up, down, right, or left, not diagonally. Now guys, basically let's try to find the city block distance between given points, between the points that, or let me just use these points here. But then here, instead of Euclidean, let me use what? Let me use a city block. City block. And then here I'm gonna change it to city block. And then what I do, guys, let me run the codes. And then guys, basically you can see that it has printed out 11. Basically guys, this is how you can find the city block distance between these 2 points here. Now let me talk about the cosine distance. And basically guys, this is the value of cosine angle between the 2 points, perhaps point A and B. And let me just use the same values here. And then here, instead of city block, let me just use cosine. Let me use cosine. And then what I do here, instead of city block, let me use cosine. And then let me run. And then guys, basically this is how you can find the cosine distance between these P1 and P2. Now let me talk about now the Hamming distance. And basically this is the proportion of bits where 2 bits are different. And it's a way to measure distance for binary sequence. Guys, let me show you an example to find the Hamming distance between given points. And guys, here let me change it to Hamming. And then here let me change to a Boolean value here, like true, comma, false, comma, true. And then here let me say perhaps false, comma, true, comma, true. And then here let me change it to Hamming. Then guys, what I do, let me run the codes. And then guys, this is how you can find the Hamming distance between these 2 points here. So guys, basically this is all about spatial data that I wanted to show you in this tutorial, and I think you've gained something. Please consider subscribing, like and share this video to your friends. Until next time, this is Nehemiah. Goodbye.